Yeah, first a disclaimer to the audience in the video. I usually don't allow putting any presentations to public internet without really a lot of polish. And I'm giving this talk for the first time, so don't expect too much. So watch at your own risk. But so, why I'm talking about this, Sami Kaski basically invited me. I think there are some professors who have more experience, at least in particular subsets of this topic, but I guess I was kind of invited as a sort of ambassador or bridge builder between the science and design communities, because I have both technological and art degrees. I've studied in former Aalto Arts before Aalto, and then did a doctorate at TKK, so the current computer science department of Aalto. So I've been on both sides. My professional history, I was a game designer and programmer for a while, or that was my first real job. Then I had a kind of period of being a media artist. We toured a lot with some interactive installations. So they were kind of game/learning tools. Then I spent, and that was at the same time I did my doctoral studies, and then I spent 6 years in the industry as CTO of a game startup. Then I became a professor, and now there's another spin-off, but I'm not really much hands-on involved because the professorship requires all your time, and I also know from history that being in a startup requires more than all of your time. So it's really hard to marry them both. Some examples of stuff I've done. This was basically I've done in the game design or design side. I've done embodied interaction design. So for example, this was a full body martial arts computer vision based game. Here's a short clip of it in action, showing only one screen. So it was this kind of empowering, or designed to be empowering experience that integrated game physics and computer vision in a way that kind of made you run faster, jump higher, gave you slow motion replays of cool techniques, kind of trying to make you feel as badass as possible. Then this is a later thing that many of you might have seen in your social media feeds. This was a research project, and now it's a spin-off. So now called ValoMotion, and this is the Valo climb system. They have now some new products as well. On the AI side, or why I'm semi-qualified to talk about that, is I've done work on movement AI. So basically continuous control optimization, like this was our first breakthrough paper that allowed this simulated, so it's a physics-based simulation or simple biomechanics simulation. There's no movement data. Everything is based on real-time Monte Carlo optimization of the movement trajectories and some efficient simulation. So basically you define goals like stay in this ready stance, and then everything emerges from that. It has to dodge the flying projectiles and so on. There's some more later work that kind of integrates this kind of short-term, short horizon planning of movements with the kind of longer-term strategical planning that is needed to solve climbing problems. Like here, the problem definition is we give the agent a body model, we give the holes and said, okay, you have to start from these and get to that. And then this movement emerges from that. All right, intro done. Let's get to actual content. So first, some definitions. So what is design? Of course, I had to look it up because there's many definitions. This is the Oxford English Dictionary definition. So as a noun, a plan or drawing produced to show the look and function or workings of a building, garment, or other object before it's made. This is kind of the historical meaning of design. So basically meaning industrial design, some object, crafting an object. But then in a more generic sense, like it's now used to, there's design thinking, there's service design. Design can be anything. basically planning something. And as a verb, I think this is kind of, well, that's the old one. Again, it talks about objects and garments. But I think this is the most generic one. Do or plan something with a specific purpose in mind. So, of course, that can kind of include both artistic work and engineering work. So if you talk about design with people who call themselves designers or artists, I think the distinguishing factor is that design is experienced by people. So it's not, so that specific purpose is defined in terms of the effect of your design on people. So basically user behavior and or user experience. So designers often basically define a target user experience in terms of emotion, for example, and then they try to achieve that emotion. And basically quantifying this goal attainment, so if you think of it as optimization, how you evaluate your objective function, you need to predict or measure behavior and experience. And such prediction is never perfect. That's, when you design a game or something, you have a kind of picture in your mind of what the player would do. But when you then make a prototype and give it to actual player, everybody does something different and usually quite something else than you predicted. So that means that getting things right requires iterative design, implementation, and evaluation with users. Just a kind of side note that this implementation and iteration can also be part of the creative process. It's a way of introducing noise that can then lead to eliciting new ideas. An example of how target experience is defined. This is an award-winning, very successful game Journey, but the designers kind of define that they want to create this kind of dramatic development over the game. So this here, the vertical axis is emotional intensity. So it kind of starts with kind of neutral, then there are highs and lows, and then a climax at the end. And then the designers were inspired by drama and narrative theory, like the monomyth, Joseph Campbell's thing that also is behind Star Wars movies, for example. And also they basically implemented psychological principles such as everything is perceived and judged relatively in relation to the spatio-temporal surroundings. So the climax at the end, to make that feel like a climax, it requires this low before that. And it's really interesting. I tried to find, at the last minute, I tried to find screenshots, but how many of you have perhaps played the game Journey? Great, one. Well, I didn't expect that many, but it's basically this kind of meditative experience, non-competitive. It's not really focused on challenges, for example, and it's really interesting that this low there means that you basically deprive the player of agency and power. So the character kind of is ascending through a snowy mountain with wind blowing against him or her. Well, I don't actually know. And the moment when you push your gamepad forward, it gets slower and slower, and it feels like, oh, what's happening? And then finally, kind of, it fades to white or white out. And then you kind of wake up at the finale where you have all the abilities you have acquired through the game, unlimited energy to fly and do all kind of empowering stuff. So alone, this part would be like meaningless. It's not really interesting gameplay, but when you add it to this whole dramatic arc of the game, it very much heightens the final kind of cathartic experience. Right. I said that design is iterative, so let's talk about design processes. So if you Google up design process, like I did for it, just illustration, there are kind of various ones, basically all design thinking, consultancy agencies, they have their own processes that they sell. But the common thing is that it has some iteration where you do some research, you create something, you test something, and then you rinse and repeat. So it's kind of glorified trial and error, like Antti Oulasvirta likes to say, that we should move beyond trial and error. But, well, more about that later. And another characteristic is that these design processes explore and prune. So here's a classic Lassow's funnel. So basically in the beginning you create a lot of ideas. You are in the elaboration phase. But then at some point you start to reduce, especially since creating ideas like sketches and stuff is cheap, but actually producing them is expensive. So due to resource constraints, you start to need to prune what you actually implement and test. And then there are variations of this theme where you kind of do multiple cycles of this expansion and reduction. You could also, as computer scientists, and I like to think of it as a tree search. So you kind of try out different options for some depth, and then you backtrack and you move forward with the most kind of promising ones. And this model also helps, at least me, to think like, how can we make this more efficient? Because in tree search, there's kind of specific ways you can help it. But okay, a bit more generically, where do AI and machine learning fit in the processes? So first, you can think of the beginning, initial ideation. There are a multitude of creativity tools. They have been around, basically some kind of random generators. They have been around for a long time, but now with modern generative models like GANs, they are becoming more powerful. So you can generate game names, synopses. You can sketch interactively so that you start sketching something, then you use some kind of condition a generative model with that, and it gives you some suggestions, completes the drawing or transfer them. Then the design goals itself can be subjected to generation and optimization methods. This basically affects your tree search depth. You want to scope your design so that you can actually reach the goal. And you want to select the goals so that they kind of serve your target group or make commercial sense or whatnot. So there's, for example, AI startups that sell these kind of services where they try to predict the game's review success based on some initial list of attributes that the game has. And then you can use that to kind of iterate your design goals, for example. Then obviously in the tree search process, you are at the point where you need to kind of decide what are the things to try out. So you can use AI techniques to generate good candidate solutions. So you can basically do more informed trial and error, so reduce the branching factor. And when you actually take that branch, you need to implement something into a prototype and test it with users. So here again, you can use, for example, neural network tools that convert quick sketches to final images, or texture synthesis, or what we do in the animation research. We make creating character movement easier, so that if you want to create a game prototype, our goal is that you shouldn't need to kind of book a motion capture studio, book actors, do that, and you just define the goals for the animation, and then you're good to go. And finally, you can also evaluate candidate solutions with user models, and even optimize the whole thing, which kind of requires that all the above is automated. So in the last part of the talk, I'm going to talk about optimization, because it's a kind of natural thing. And here, this is a model from Antti Oulasvirta's kind of, well, it's in the IEEE computer. It's kind of a position paper or kind of summary paper on this, how to optimize or view user interface design as optimization. So it's fairly good fit for design in general, although, for example, this behavioral scientist is, well, that's a bit narrow. You might need other than behavioral science in defining the user model. But basically the model is that the designer defines the task or goals, then there's some optimizer, then some user model, and these run in interaction, and then the designer kind of checks what kind of results are coming back and reiterates on the goals and so on. And you typically need a computer scientist to define the optimization task or operationalize the design goals. And then maybe you need psychology, behavior science, ergonomics, all kind of human sciences to inform the user model. So basically, this is a way of, when you design, you're searching a design space or optimizing design parameters to maximize the attainment of design goals. And then the problems, the hard things are how you measure and quantify the attainment and define the goals. Let's take some examples of what is tractable. So again, Antti Oulasvirta's paper. So basically, Antti's group has done a lot of things already. The most well-known thing is probably the French keyboard. So you can optimize keyboard layout based on what you know about the language that you want to type, so the statistics, what are the frequencies of different words, different characters, and then some models of basically human motor control, how slow it is to move between different characters. So starting from basic things like Fitts law, which predicts what is the kind of relation of, when you do kind of targeted movements, what is the relation of your target size and the target distance to the acquisition speed. Antti's group has also done, for example, scatter plot optimization, so how to automatically basically manipulate the intensity or opacity of the plotted stuff so that you can kind of see the structure, because this is what you get if you kind of just say scatter in MATLAB by default with this data, which is really complex. Then in Aalto Arts, on the architecture side, there's a lot of computational design of architecture. So Toni Kotnik is the computational architecture professor, and this is one of his student work. So basically bridge optimization, where the designer, I guess, defines the aesthetic by constraining the set of primitives. So for example, in this case, it's a specific type of parametric curves that should make a shape or structure that kind of can withstand load. And then it's also kind of automatically create something aesthetically pleasing because of the properties of the curves. And this term form finding is the key if you want to learn more about architecture and computational methods. So there's a lot of literature, books, and papers. But I'm not really an expert on that. That's just something I kind of searched for this talk. My field is games, and there we have a lot of work, in particular in procedural content generation. And this is a nice book that gives a comprehensive overview. It's freely available at pcgbook.com. And for example, if you think of generating content as an optimization problem, this book divides the ways to evaluate the objective function into 3 categories. There's direct evaluation, which means you have some kind of theory-driven or data-driven model that just gives you you give it the design parameters and it gives you the objective function. Or then for dynamic experiences, you may need simulation-based evaluation. So basically, you create a game and then have AI agents play the game. It's kind of the most generic way of automating this objective function evaluation. And I think that's also the future, which I'm going to elaborate later. And then there's interactive evaluation, where you actually don't use a computational model, but you use humans in the loop. And this is the state of the art right now. It's actually happening in the industry too. So in King, the maker of Candy Crush games that make millions every day, so these match 3 puzzles where you try to kind of slide these tiles so that, for example, if you slide this one here, you get 3 and they explode and you get points. So King has started to do playtesting with deep learning. And they basically say that the benefits are that the designers can do this playtesting at a shorter turnaround, so they get feedback more frequently and with less delay, which leads to more more optimal content when it's actually released to players. So of course you can never replace the players entirely, but you can kind of do initial design iteration this way. Yeah, in this case, they tried different things like Monte Carlo tree search, I think also reinforcement learning, but in the end, because they want human-like data and they have tons of that data, because they have millions of players, so they did just supervised learning of what the player does, kind of stimulus response model. What would the player do given this puzzle of some 12 million games played? So if you don't have a computational model, internet provides ways to scale this up. So also, again, in games, we have a lot of these companies that offer online testing services. So you can just fairly affordably launch your game and have it played by as many users as you can pay for. So Playtest Cloud is used by many Finnish mobile game companies, for example. But what are the problems? Basically, for hard optimization problems, the cost of real users is too high. When you need so many objective function evaluations, or many evaluations, because it's a hard problem and the search space is huge. And then these data-driven simulation models like King uses for Candy Crush, they are limited because they need the data. So you can't apply them before you have the product. They don't generalize to new designs. They don't generalize beyond the variables of interest that you collected for your data set. So if you come up with, hey, okay, this would be a nice thing to model, well, then you have to collect that 12 million games again. And, okay, forget that last bullet point. I should have removed that. So let's take some examples of these harder design optimization problems. This is kind of an experiment I did, taking some fields of design, something cool, trying to kind of reverse engineer what was probably the objective function that designers tried to optimize, not computationally. But these are the things we should learn to solve. So here you could think of fashion design. For example, this is from Aalto's fashion design graduate collection show from last year. So there's, you try to maximize some kind of aesthetic impression that can be broken down further. Then you maybe try to maximize media virality, but also to some degree wearability. So always kind of balance between practicality and show. Project Runway, a great fashion design show. So this reality TV show where fashion designers compete, that gives the designers very specific challenges. For example, and usually the goal is to maximize judge scores, but in every challenge the constraints change. So here, for example, the constraint was, I think, the budget must be less than $300 or something like that, and all materials must be bought from a specific candy store. So these are all made from candy or candy packaging or something like that. So then in game design, often we try to find, if you don't have a budget, unlimited budget for creating something like Battlefield or Fortnite, you try to kind of create a small unique game with a so-called design hook and try to kind of operationalize what the design hook means in terms of an objective function would mean to me that you kind of maximize novelty. So it's something new players haven't seen, and curious interest in this novel game mechanic, like the portal mechanic in Portal. But at the same time, you have to adhere to genre best practices like known control schemes, so that players are not totally lost, and also you want to provide meaningful challenges, because often if you do experimental gameplay, it can feel kind of arbitrary, and it's hard to build a steady progression and so on. In this case, this is a Kickstarter video of game Strafe. Okay, I don't have sound. We have sound somewhere. Start again. And now do we have sound?
No, still no.
Very faint. Well, anyway, so as you see here, the game was really kind of this kind of super retro, really simple kind of Doom clone, or at least that's how it looks. But then the designers made a really clever choice of focusing on the reactions of kind of hypothetical players. So they kind of communicated this feeling how awesome it would be to play this game and use this product. And it's just a fantasy thing that they sell, and this video and the Kickstarter campaign became a huge success, netting many millions, I think. So it just tells the story that this is a game you just must play, and then it will suck you in and destroy your life. At the far end from that in games journey, again, like I already mentioned, there the designers had this overall goal of maximizing the feeling of kind of tranquil awe, the sense of awe, and this kind of, like you see, it's mostly you walk alone. Sometimes you meet somebody, other players, monsters, but it's very kind of meditative. And sometimes the target is not even positive emotions. So for example, that Dragon Cancer is a game about, kind of autobiographical game about the game designer's son who died of cancer and goes through the whole kind of grief process, or the story of that family. So it's a game about empathy and grief, but still somehow it's very kind of satisfying, and it was also a commercial success. So this is really, we go into kind of deep waters here. Another game in the same kind of, not genre, but bit same style is This War of Mine. Again, it's a game about bad stuff and negative emotions. So how you survive and live in war zone. You can think of Aleppo, for example. And this is a game about reflection, and maybe the insight here is that user experience is not limited to the product use, so it also kind of lingers on after that. So you play that game, then when you are in the metro to work, you start thinking about that and what are the things you learned and what are the emotions, and that's what kind of makes it satisfying. One last game example, sandbox games like Minecraft have perhaps the most generic and ambiguous goals. So here, it's an open-ended game. So you don't have goals and you don't have rewards, but at the same time, you want to make the game feel satisfying and meaningful. So how to do that? It's kind of, yeah, you need psychology of intrinsic motivation. And this is kind of my own field, something I'd really like to be able to generate automatically synthesize. So how you, for example, design playful geometry. So something that is really simple and like this plate, steel plate, but at the same time it arouses curious interest and engagement, or elicits movement play, both in animals and humans. All right. I lost my timer. What's the time now? Okay, we could end here. I'll go for 5 minutes. Okay. So thinking of all these hard problems, so what is the kind of design process that applies to them all? I guess it's this kind of really simple one where you have a designer that's feeding some ideas, prototypes, questions, then getting feedback from users. It may be the initial kind of interviewing or observing users living their life and then thinking of, okay, what are the ways to improve? Or it can be specific focus group testing, play testing, all that. So I think if we want to empower designers, the user modeling side is really the key. So how can we kind of make it possible to use both simulated and real users, or computational models of users with real users? Because that doesn't take away agency from the designer. You cannot say that you are optimizing away anyone's job, it also removes the kind of busy work, the grunt work of recruiting users, collecting data, videotaping, annotating, everything. So this is kind of the way to go. So what would be the future of user modeling? I mentioned already there were some problems, for example, with data-driven models. And I think that the way to go is, through optimization. So basically, can behavior and user experience emerge from optimization? Well, it seems it can, and we are there's an emerging trend and nice recent progress. So basically, on the cognitive side, so for example, rational problem solving, deep reinforcement learning now handles complex actions, and also you can apply it to embodied models. So you can have simulated bodies like we do in our research. And when those models develop and evolve, you can quantify ergonomics and various other user experience factors through that. It's also fairly trivial to employ bounded rationality. So of course, humans are not perfectly rational. Or it's not trivial, but at least some degree of predictive power can be had by simply, for example, using limited computational resources, like limited Monte Carlo tree search sampling budget or limited size neural networks. There's some papers on that in games, at least, where player skill levels were simulated with just that. And then there's recent work that increasingly gives evidence that motivation and emotion can be integrated in reinforcement learning or behavioral optimization as reward maximization, such that you can make plausible behavior emerge, for example, curious exploration, when you don't have any explicit rewards, when you don't have data-driven behavioral models. And at the same time, through the kind of internal workings, you can also quantify and log how the user experience evolves. For example, how your curious interest towards the product evolves. And there are similar initiatives in other fields, like this whole kind of virtual humans. I think that's a really grand challenge for computer science and simulation. So this is the virtual physiological human EU project and some kind of research community. Basically, they try to simulate the physiological stuff, so how drug molecules interact with the body, basically, so that then you can do kind of exploratory drug optimization with these simulation models. So just a few closing remarks. So how you do that? Basically, the good old reinforcement learning provides a good framework. So reinforcement learning was inspired by early behavioral psychology, and the basic model is this, that you have an agent taking actions, getting some observations and rewards. And the goal is to maximize those rewards cumulatively over time, or the expected rewards. And it's also, as a kind of interactive cycle, it's good fit for interactive user experiences. And you can, in game testing, for example, you can test whether the puzzle can be solved, what is the level of difficulty, alternative strategies. So here's a classic example of my field, movement optimization. It's a half cheetah. So that's the kind of gait that emerges when, or most of the time, when you try to kind of maximize going forward. But then sometimes the optimization finds these somewhat surprising strategies that the designer didn't anticipate. In this case, the designer is the one who designs the reward function. So that is what happens. And these insights, okay, hey, you can actually hack the system this way. These are very interesting in game design also. So for example, one example I heard was in a first-person shooter game, the AI designers didn't want the AI to make unfair. So they created a rule that AI never spawns behind the player. Well, what is the exploit that you get from that? You can actually speedrun the game backwards, because there's never going to be enemies in that direction. So they found that quite late in playtesting, but I'm sure if they had reinforcement learning or any kind of optimization-based agent, they would have discovered that earlier. Some other examples, you can kind of test gain balance, so how different characters match against each other, so you can create this so-called intransitive balance of rules of rock, paper, scissors. But then many games are much more than simply competing or solving problems, Minecraft being a prime example. So we need AI models that also model human motivation and emotion, and which should allow the emergence of things like social sandbox play. And how you do that? We did a literature review last year. So the dominant paradigm seems to be something like that you integrate this kind of motivation and emotion module and divide the reward function into extrinsic and intrinsic. And this way, the intrinsic reward, you can think of that's kind of your neurotransmitters, dopamine and oxytocin and something like that, very roughly speaking, if some psychologist is watching. And this way you can kind of integrate both intrinsic and extrinsic psychological motivation theories into this optimization framework. And also you can have state here which leads to kind of emerging emotional and motivational dynamics. So for example, curiosity is a good example of that. So this is some practical results. Psychologists model curiosity or curious interest as an emotion comprising two main appraisals. For example, the appraisal of novelty, that your stimulus is novel, and then comprehensibility / coping potential. So you at the same time, it cannot be as so novel as to be kind of incomprehensible or frightening or something like that. In this paper, they implement this novelty in terms of prediction. So the agent tries to predict the results of its actions. And if something unpredicted happens, it gets an intrinsic reward. So it learns to explore those better. And then there's some tricks to make it not kind of try to predict white noise, for example. And that video I don't have here, but it's really awesome follow-up piece where, yes, if it's white noise, it doesn't get curious. But if you introduce a video screen and give the character a remote, then when it encounters that video screen, it will stay there and always switching the channel because there's always some kind of random, unpredictable new TV channel appearing. So it kind of models this couch potato behavior. Right, I think I have to stop here. I had some other stuff about basically need satisfaction and stuff, but I'll leave it here, the future work, and take questions now.